minus square root of 2 divided by 2 squared plus square root of 2 divided by 2 squared plus 3 divided by 4 squared. Okay? So this is your potential function evaluated at the initial point. All right? So the only thing I need to do is to find the function difference between these 2 points. And these guys are all canceled out. So in the end, I'm just taking the difference between 7 divided by 4 squared minus 3 divided by 4 squared, and then divided by 2. So I have a 49 minus 9, I have a 40 divided by 16, and then divided by 2. So in the end, I got a 5 divided by 14. Okay? So which is exactly the same number we have from the line integral. Okay? So I give you 2 examples to evaluate and to verify the fundamental theory of calculus. In the first example, the curve itself is actually closed, which means the line integral of a conservative vector field is always equal to 0. In the second example, we're taking the line integral of a conservative vector field along an arbitrary curve, which is given by a helix. And then the line integral is going to be equal to the function difference of the potential function at the initial point and the terminal point. Okay? Questions? Now, I want to modify my problem a little bit. So I still have the same vector field. And I say C is a curve from minus square root of 2 divided by 2, square root of 2 divided by 2, and 3 divided by 4. 2 square root of 2 divided by 2 minus square root of 2 divided by 2, and 7 divided by 4. Okay? So listen to me carefully. Here is my problem. I have a vector field, and I have a curve. I don't know what it is, but I know it is from a point to the other point. I still want you to compute the line integral of this vector field along this curve. How do you do that? If I ask you to evaluate a line integral, usually I have to give you what the curve is. Am I right? Usually I have to give you the precise information of the shape and where this curve is lying at. So if in a problem, I don't give you any information other than the initial point and terminal point, I still want you to evaluate the line integral. What the hint can I get? If I don't give you any information of this curve other than its initial point and a terminal point, I still want you to evaluate the line integral. This can only be done if the vector field is conservative. Am I right? If the vector field is not conservative, I have to give you what the curve is. If I don't give you any information of the curve, I still want you to evaluate the line integral. This is only possible if the vector field is conservative. Because if the vector field is conservative, then the line integral is independent of the curve. Am I right? It is only depending on the function difference of the potential function at the initial point and terminal point. So as long as these 2 points are given, you can always evaluate the line integral, no matter what the line it is. Are you with me? Is this confusing to you? Okay? What's happening today? You guys are not very excited today. Actually, the material is actually, material-wise, is actually more interesting than the double and triple integrals, I have to say. Right? So which means as long as I have 2 points, one point is dipped at my initial point, and the other point is dipped as my terminal point. I don't know what the shape of the curve looks like, but as long as this vector field is conservative, I can always find its potential function and directly evaluate it at these 2 points, and that's sufficient to get a line integral. Are you with me? So I don't have to go for the parametric equations and then stick in my t variable and do a single variable integration. Because on one hand, you cannot even do that. The curve is not even given, right? So you have to go for the second route. Are you with me? So if I'm getting a problem to evaluate a line integral of a vector field without giving you any information of the curve, this is a big hint that this vector field has to be conservative. And then you try to find the potential function. How to find the potential function? We have all the universal tools to deal with that. And then the only thing you need to do is to evaluate the boundary points. Okay, and that's it. Okay? So I want to ask you, as long as we finish doing this, what do you think we should move forward to? Yep. So the potential function is a scalar function. Am I right? You agree with me? The potential function is a scalar function, which means I'm evaluating at two given points. This is a number, this has to be another number. So in the end, I definitely get a number. That's the line term. Okay? Is that what you're asking here? Mm-hmm.
Are we still going to be using the x squared?
Yeah, exactly. We're still using that because the vector field is still x, y, z. The potential function is the same potential function we have over here. Okay? So if you finish this conservative vector field discussion, what do you think we should move forward to? If we have the line integral of vector field, if the vector field is conservative, we have all fundamental theory of calculus. So a very natural question you can ask yourself is, what happens if the vector field is not conservative, right? So that's a very natural question to ask. If it is not conservative, then the business is going to be trickier, but we can still deal with it. So this is the whole business of so-called Green's function, or Green's theorem. So Green's theorem, what I understand is the fundamental theory of calculus of vector fields in R2. Okay? Here I don't have any restriction about whether they're conservative or not. Any given vector field. But I want to begin from easier case, which is the vector field in R2. So in R2, I still have any given curve. But now I want to make it even simpler. I want to have a closed curve, smooth closed curve, orientated in the counterclockwise direction. So this is my C. C is a closed, smooth curve. So orient counterclockwise. Okay. So this is my setup. I want to compute a line integral of a vector field, not necessarily conservative, with respect to a closed curve. Okay? So again, I want to ask you again, if this vector field is conservative, what's the answer? Zero. If it is not conservative, then the answer is not necessarily zero anymore. But what is it? Okay? So this one, first of all, I can rewrite it a little bit. So f as my vector field in R2 has two components. So my f is equal to f and g. So I can rewrite this representation by writing g dx plus, f dx and g of dy. This again is just a slightly different notation. By writing vector field as a small f, small g, and dr as dx dy. So this essentially is just a slightly different notation by expanding fg as a vector dot product with dx dy. And that's why I'm getting f dx plus g dy. So this is just nothing but a notation. You don't have to be very cautious about this. You don't have to use this in your writing. So otherwise, I'm writing this only for the purpose that if you have ever seen this kind of representation, it just means a line integral. That's all. Okay? So this is just a line integral by expanding your vector field as fg as a vector and your curve as a vector dx dy. So when you expand this dot product, you're getting exactly f dx plus g of dy. So this is just another writing of the line integral. So the Green's theorem says this guy is nothing but a double integral in the interior of the following function. partial g partial x minus partial f partial y. Okay. This is so-called fundamental theory of calculus of vector fields in R2, which is a generalized version of the conservative vector fields. Okay. So it is a generalized version of the conservative vector fields for one simple reason. As long as this vector field is conservative by using Green's formula, this guy is indeed equal to 0, am I right? What do we mean by vector field is conservative? The symmetric derivatives are equal to each other, so gx is equal to fy, so this guy actually disappears. So that is why it is generalizing our original conservative vector field fundamental theory of calculus. This one works for any vector field, even though it is not conservative. The only thing you do is to compute whatever this formula is. You compute whatever this formula is, and then you take the double integral in the interior, you're getting exactly the line integral on the boundary. So as long as this is about the two integrals, one is in the interior, the other one is on the boundary, this is falling into the general realm of fundamental theory of calculus. Okay? So I'm taking the double integral in the interior, it equals line integral on the boundary. So this is the fundamental theory of calculus. And this guy here, partial g partial x minus partial f partial y, is denoted as the curl of the vector field. Okay, is denoted as the curl of the vector field. CURL. Okay, so CURL can be understood as an operator. You put in a vector field, you're getting a scalar function. Okay, so curl is a vector field as the input. Then you're getting a scalar function as the output. Okay? You put in a vector field here, you're taking the symmetric derivatives, and then you take the difference. You're going to get a scalar function. Okay? So in other words, the line integral of a vector field on the boundary is equal to double integral of the curl in the interior. In the special case, if the vector field is conservative, then the curl of the vector field is automatically 0. That's why the double integral in the interior doesn't give you anything. It's just the 0. And the line integral on the boundary, as long as it is closed, is always equal to 0. Okay? So this fundamental theory of calculus of vector field is extremely powerful. It is extremely powerful for the following reason. If I'm computing the line integral on the boundary, if the boundary is very complicated, I don't have to stick with the line integral. I can actually do a double integral in the interior to find the line integral on the boundary. All right? So I can use a double integral in the interior to evaluate a line integral on the boundary. This is one of the applications. The other application is now we have one additional tool to evaluate the double integral. We have one additional tool to evaluate double integral. Double integral, we can go for x simple, y simple, polar, r simple, change of variables, and then line integral on the boundary. Okay? Not only I can use all the previous tools to evaluate double integral. If the region you're looking at is too complicated, however, you have a very nice boundary, you can still compute the double integral by computing the line integral on the boundary. And this is extremely useful. This is extremely useful for the following reason. Imagine if you are evaluating something in the interior, which is a lake or anything, you cannot really get into that. But this formula will give you an alternative tool to evaluate what is in the interior. You just need to walk around the lake for a whole round and get what is inside. Now with me, you don't have to get interior in order to evaluate a double integral. As long as you can walk around the interior for a whole round, you do a line integral. The line integral is easier to compute in some cases. In applications, this is what the engineers do, a lot of the geologists do. As long as there's not possible, you can get in the interior. You can still compute something on the boundary to get the information in the interior. So imagine this is an extremely powerful tool you can use, right? This is extremely powerful. So I want to give you a couple of examples, maybe one for today. So let's look at this example. we always begin from the easiest field. Okay? And R is equal to x squared plus y squared is less than or equal to 6. Okay? So the only thing I want to do here is to represent both sides in the Green's theorem. So remember, on Green's theorem, there are two integrals. One is the line integral on the boundary. The other one is the double integral in the interior. So simply, I'm just writing down what they are in this particular example. Okay? So I have a region which is given by a disk, right? So I have a region which is given by a disk. So the boundary is going to be a circle, and we always orientate it counterclockwise. Okay? We always orientate it counterclockwise. So the double integral in the interior is with respect to the curl of the function right here, or the curl of the vector field here. So according to the formula, so if I have the boundary at C, f dot dr has to be equal to a double integral of r partial g partial x minus partial f partial y in the interior. Okay? So this vector field is extremely simple because it is indeed a what's the word I'm looking for when I discuss the property of a vector field? The number one property I wanted to know whether it is a conservative. This guy is indeed a conservative, so actually both of these two sides are equal to 0, right? But I just wanted to rewrite these two sides to give you the idea of what this theorem is talking about. The right hand side, I'm taking the double integral in the disk. How do you write it down? A double integral in the interior. If the domain is a disk, we're using the polar coordinates, right? 0 to 2 pi, 0 to, be careful a little bit here,
Radical
so 6. Partial g, which is my partial 4y here, with respect to partial x, minus partial 4x, partial y, but I have to rewrite it in the polar coordinates, which is r, dr, d, theta. All right? So this is my 4y